So, in today's lecture, we take one more example on absorption before moving on to this distillation, okay, the second unit operation for this course. So, this example will also address some of the fundamental aspects of absorptions. So, let us see this example here where we have a packed column. So, this is a packed column. All right, and this is the gas in at a flow rate of 10 kilomole per hour per meter square. So, note this superscript here prime because the flow rate is expressed in terms of meter square per meter square of cross sectional area. So, this is a packed bed absorption column. This gas contains 8% of certain gas, let us say sulfur dioxide, which means Y1 is given as 0.08 mole fractions, and capital Y1 can be calculated to be 0.087, okay, and G prime is the total flow rate 10 kilomole per hour per meter square. So, we can have molar flow rate of the solvent or the solute free basis at G prime 1 minus Y1 equal to 9.2 units. So, this units is same as what we have written here 10 kilomole per hour per meter square. So, this gas sulfur dioxide has to be cleaned with a solvent, pure solvent here, and the flow rate of the solvent is L prime 30 kilomole per hour per meter square. So, again make a note of this superscript L prime because we are writing this flow rate in terms of per meter square of cross sectional area. It is a pure solvent. So, X2 equal to 0. It is given as 97% of sulfur dioxide has to be removed. Which means Y2 can be calculated as 0.00261, all right. So, this is 97%, that means 0.087 multiplied by 0.03, 97% of removal. So, remaining is 0.3%. So, we have Y2 and then we can write capital Y2 very close 0.026. So, this is level 2, this is level 1. And the spent liquor gets in here at certain mole fractions x1 and capital X1. Okay. Equilibrium is given this time as an expressions as y equals 2.5x plus 4.5 x square. So, this is the equilibrium curve. We have to answer the certain questions here. First, calculate minimum solvent requirement. So, this problem we have addressed in the earlier lecture also. So, we calculate minimum solvent flow rate, that is one. What is the concentrations at the exit of spent liquor? So, this is X2. What is the mole fractions here? X1 actually. So, this will become, this is your X1. So, this is level 1, X2 is 0, pure solvent. And the third question is calculate absorption factor A at the location where X is 0.02. So, where the mole fraction is 0.02, this is 0 here and some values here. At the locations where the mole fraction is 0.02, calculate this absorption factor. And the last question is also calculate individual gas phase mass transfer coefficients. So, what is a small kg equal to at the same locations where x equals 0.02. We have also been asked to calculate del x del y, the driving force for mass transfer. Driving force for mass transfer. All right. Okay, let's do one thing. Let's redefine this this problem here. So we have, let's calculate this. Just calculate driving force for mass transfer based on this gas phase. Okay, and the given quantities are Kx or Kl as 1.2 kilomole per meter square per second per del x, and Ky Kz as 0.15 kilomole per meter square per second per del y. Okay, and all of this at the same location at x equal to 0.02. So all we have done, let's start here. We have marked our coordinates y1, here we have x2, here we have y2. We know this equilibrium curve. All we are supposed to do it, draw this graphically. Okay, so let's draw this graphically. Let's do it graphically. We have capital X and capital Y. All right, so that's the way we have been working, trying to plot, do the calculation based on solute free basis. So if we have equilibrium curve given as small y equals 2.5 x plus 4.5 x square, we can write as y over 1 plus y equals 2.5 capital X over 1 plus x plus 4.5 x over 1 plus x square. All right. So if you recall, in the last previous all lectures, we said that all the problems of absorptions can be done by graphically, or one can solve analytically. All right. So even if you solve analytically, it's a good practice to draw the graph and do and mark the points, salient features, at least qualitatively. Okay. So after doing this, then you can take your decision whether you want to solve graphically or you want to solve analytically. Sometimes it's easier to solve graphically, and sometimes it's easier to solve analytically. So let's do that. So this, we can draw this equilibrium curve. All right. So this is the equation. We have drawn the equilibrium curve here. Let's mark the point here. We have capital Y2 as 0.00261 at x2 equal to 0. So we have marked this point, and y1 is given as 0.087. Okay. So the first question asked was, what is the minimum solvent flow requirement? That's very easy to find out. If the shape of this curve is convex down, that means we can draw this curve intersecting this equilibrium curve here. This will give us the concentrations of a spent liquor maximum. All right. So this is the maximum. We have L by GS. So this will give you highest concentration we can have in the spent liquor, corresponding to this minimum LS by GS flow rate. Okay. So this X max from the graph, if you plot it, this will turn out to be around 0.31. Okay. So one can solve graphically, and if you want to solve this numbers analytically, all you have to do is take this equations, operating line intersects and solve together with this equilibrium curve. You can think that you can see right here that solving analytically may be a bit cumbersome because the equation is quadratic. One has to do some iteration here. But if you plot it carefully on a graph, you should get this result immediately. The point where this LS by GS minimum curve intersects with equilibrium, that will give us X max as 0.31. Okay. So from here, LS by GS, the slope we can obtain LS by GS minimum. If we know this slope, I leave this as an exercise. One can obtain LS prime. So note this here. So far we have been used to plotting LS by GS, but LS by GS is same as LS prime over GS prime. So this is kilomole per hour or per second. This would be kilomole per hour per meter square. So, cross sectional area of this column. So, we can write LS by GS as LS prime over GS prime. So, from here we can calculate LS prime as 24.85 kilomole per hour per meter square. So, this is the minimum solvent flow requirement corresponding to this minimum slope, all right, but given is LS prime equals 30 kilomole per hour per meter square. So, look at this difference here. LS operating is approximately 1.2 times the LS minimum or LS prime minimum. So, most of the calculation in the earlier lectures we did it at 1.5, but that is all right. Here in this problem the operating flow rate is 1.2 times the LS prime minimum. Okay. If you want to solve analytically, so look at, all we have to do is we have to write down the expressions for operating line, which is capital Y1 minus capital Y2 equals LS prime x1 minus x2. So, this would be our equation for operating line, okay. And make a note here that we are using this superscript again because it is a per meter squared. So, this will get cancelled, either GS or LS or GS prime and LS prime. Now, look at here, Y1 is given to us, Y2 is known, X2 is known to us, which is 0 here, X1 is not known to us, and LS1 minimum is not known to us. So, all it means GS prime is given to us. We are supposed to solve this equations 2 with equation 1 if we want to solve analytically. So, the solution is, or the method is quite cumbersome here, all right. Of course, as an exercise you can try solving these equations together with this equation 1 to obtain the same results for LS minimum at 24.85. So, here we are making this message here that very often it is very convenient to solve graphically. You draw it on a graph, Excel sheet, or just take a graph paper, and you are careful in the drawing those, you have taken enough points for drawing this equilibrium curve. Then by taking this LS by GS minimum, one can obtain immediately this x max 0.31 or the slope of this curve, or from there we can calculate LS minimum. So, very often it is possible to solve minimum effort this graphically, but even if we want to solve analytically, it is a good idea to draw on the different points qualitatively. Okay, so, let us get back to this problem. This is LS by GS minimum, and of course, we are running at operating curve LS prime by GS prime, both are given to us. LS prime is 30 kilomole per hour per meter square, and G prime is given to us 10 kilomole per hour per meter square. GS prime is given to us 9.2. So, from this, if we can draw this line, this will give us the operating x1, which will turn out to be 0.02588. Okay. Again, here one can take this curve and one can write these expressions operating curve as GS prime Y1 minus Y2 equals LS prime x1 minus x2. GS prime is given to us, Y1, Y2 are known to us. LS prime, we know the operating 30 kilomole per hour per meter square. X2 is 0. So, x1 can be solved here to obtain same as what we obtained graphically as 0.02588. So, the spent liquor concentration is x1, and if you convert this into mole fraction, small mole fractions based on for the solute, then we have 0.02523 as a mole fraction of sulfur dioxide in the spent liquor. So, of course, for this part of the problem, one can solve analytically and one can solve graphically also. You will get the same results. Now, let us try to answer the second question, where it says calculate A, absorption factor, which is nothing but L by mg, all right, and that we can write as L prime mg prime. So, L prime is known to us, G prime is known to us, okay. We have been asked to calculate this at a locations at x small x equal to 0.02. So, make a note here that L prime will change along the column, G prime will also change with the column. L dash prime and GS prime will remain the same, will remain constant, but L prime and G prime will change. So, the question is calculate this quantity at x equal to 0.02. Okay. So, first is the slope m is nothing but dy by dx, which you calculate, differentiate equations 2.5 plus 9x, evaluate this at x equal to 0.02 or capital X equal to 0.0204 to obtain this 2.68. Right. So, now we have to get L and G. For this we require Y. What is the mole fraction corresponding to this 0.02? We make use of again operating line equations. We have GS prime 0.087 minus Y. So, this is Y2 here, or this is Y1 actually. So, capital Y1 minus capital Y equal to LS prime. Similarly, we have x1 0.02588, okay, minus just now we have calculated 0.0204. So, we have this 0.0204. GS prime and LS prime is known to us. We get capital Y equals 0.0691. This will give us mole fractions 0.0647 corresponding to x equal to 0.02. Okay. So, we can write as G prime as GS prime 1 plus capital Y to obtain 9.83 kilomole per hour per meter square. Similarly, we can write L prime as LS prime 1 plus x to obtain 30.61, and then one can calculate A equals 1.16. So, we have absorption factor, knowing slope of the curve 2.68, knowing L prime which we have calculated 30.61, G prime 9.83 at this locations where we have mole fraction is 0.02 to obtain this absorption factor 1.16. So, here also we can conclude from this example that absorption factor changes along the absorption column. Why? Because even if we have the linear curve, slope m may be constant. Here of course it varies, but in those cases where the slope changes, it is possible that L prime over G prime or L over G will change along the length, because liquid flow rate changes, gaseous flow rate changes, so there is mass transfer, not necessarily L by G ratios will remain the same. LS by GS will remain the same because individually they remain constant along this absorption length, solid free basis. So, in this example the question was calculate this absorption factor L by m over G at the location where the mole fraction in the liquid phase is 0.02. So, we have to do this calculation, we have to find out what is Y corresponding to small x. For that we wrote down the operating line equations, and operating line equation connects the bulk phase concentration given x, what is Y, knowing the flow rates. So, from there we get a small y, we calculate the capital Y solid free basis, and then we calculate L prime and G prime at that locations where we have this mole fraction equal to 0.02, slope of the curve, we know the equilibrium curve, we differentiate to get dy by dx, and we substitute this number for a small mole fraction. So, this part of things we have done it without graphically. All right. And the last part, the question is calculate the gas film based driving force. So, that is your Y minus Yi. Now, again the driving force in the columns, if you recall, it changes because mole fraction of Y changes, Yi the interfacial concentrations, if Yx changes, interfacial concentration will also change. In some cases it is possible that the difference Y minus Yi may remain the same, but nonetheless we are supposed to calculate this driving force based on the gas phase film at the location where the mole fraction is 0.02. All right. So, if you recall how we did it, again we can do graphically and also we can do it analytically. So, to do the graphically, one has to draw the slope of this time minus kx over ky. So, let us do it graphically as well as analytically. So, this is the last part of the questions, where we have been asked to calculate del y driving force based on the gas film equal to what, or y minus yi calculate at the location where x was 0.02, okay, and we calculated y corresponding to this x as 0.0647 in the previous part. Okay. So, if you draw this, want to do it graphically or even otherwise, it is a good idea to draw graphically. We have this curve of y equals 2.5x plus 4.5 x square. So, we draw this curve, and the locations where the bulk phase concentration is given as 0.02 to 0.0647. So, this is the coordinate of x and y. In the absorption column, x varies from liquid phase from x equal to 0 to we calculated the exit phase concentrations, which was 0.02588. All right, this was 0.02588, that was capital X1, but we calculated the small x1 as 0.02523. So, the locations where x is 0.02, that is what we are trying to find out. So, we have this interface and we have this yi and xi, we have y and x. So, x is 0.02, and corresponding to this x equal to 0.02, y is given as calculated as 0.0647. So, we are supposed to get yi, so that we can calculate y minus yi. So, what we do? All we do, we take the slope of this line, draw this curve with the slope minus kx over ky. So, the value of kx and ky is given to us. We take this curve on this graph, we take the slope, it intersects here at yi and at xi. This coordinate, if you do graphically, it will turn out to be yi equals 0.05477, xi will turn out to be 0.0211. Based on this, we have the answer del y equals y minus yi. Y is known, yi, this equals 0.0647 minus 0.0211. All right. Similarly, one could have also calculated driving force based on the liquid phase xi minus x. All right. So, one can obtain these results from the graph, and we must not forget that alternatively we can also solve by equations. So, writing down the equations instead of graphically, one can also calculate this xi and yi or ax or y. So, alternatively we can write down the equations. Na equals kx, xi minus x equals ky, y minus yi. Okay. So, kx is given to us, ky is given to us, x is given to us, yi is given to us. Yi and xy we are supposed to calculate. So, one equations, we have another equations, equilibrium curve yi equals 2.5 xi plus 4.5 xi square. So, now you can imagine solving these two equations analytically may be cumbersome, but as an exercise you must solve to get the same results for del x and del y as a driving force here. All right. So, again here we have made a point that there are certain class of problems which you can solve very conveniently graphically. Okay. So, even if you are solving analytically, it is not a bad idea to draw the curve and then see what is given to us, what is not given to us, what are the quantities which we can obtain graphically without doing any iterations mathematically. So, that is a question we have answered. That is first another example on absorptions. And the more important here also to note that number of transfer units one can also calculate graphically as well as analytically. So, number of transfer units, if you recall, for a dilute solutions we have a very simple expression dy y minus yi, all right. So, again y minus yi is the same quantity which you have calculated here at location 0.02. So, that y minus yi is the driving force. All it means, if you are supposed to integrate this quantity dy by y minus yi from y1 to y2, we are supposed to draw several of these parallel lines of minus kx and ky. In other words, the way you will do mathematical integrations, you will divide your absorption columns into several small sections, preferably equal sections between y1 and y2, and take those bulk phases, y1 and x1, y2, x2, y3, x3, and draw these parallel lines. So, you have the equilibrium operating line, you have the equilibrium curve, you can draw this operating the slope of minus kx and ky wherever it intersects, that gives you yi and xi. You can do the calculations for NTU based on the gas phase, dy by y minus yi or dx by xi minus x integral from now x2 to x1. Okay. You will get a number of transfer unit based on the gas phase, number of transfer based on the liquid phase, multiply by respective height of a transfer unit based on the gas phase or height of a transfer unit based on the liquid phase to obtain the same or height of the column. Okay. So, just to sum up here, the same curve, since we are talking of driving force, let us again try to understand the meaning of this NTU. So, we have NTU as dy by y minus yi, y2 to y1, all right, y2 to y1. So, this is what we have calculated, this is a driving force of mass transfer based on this interface. So, we have dy and del y. So, we have this equilibrium curve, you have the operating curve, you have you have the boundary here y1, you have the boundary here y2. You will divide this y1 to y2 in several dy, all right. So, you will take several of such sections, maybe 10, and obtain this. So, you have y1, y2, y3, y4 between these two domains, and from each lines you will draw this parallel minus kx minus ky etc., the slope minus kx over ky to obtain yi corresponding to this y1, another yi corresponding to this. So, we have all yi's, and then we can do this calculations for number of transfer units. You will make a table of yi here, then you will have del y or y minus yi, you will have del y over y minus yi. Del y need not be the same, in other words this can change here. It is a good practice to keep it uniformly between two domains y1 and y2. Then you will take several such points 1, 2, 3 etc., maybe 10, and if you add all this summation of this column to get you NTU, number of transfer unit based on this gas phase y. So, this example also very similar to this, it is a graphically here, you draw a graph here and draw these parallel curves. Be careful with the drawing these lines, you have to be extra careful so that you arrive at a numbers which is very accurate, all right. So, this is the end of our lecture on absorptions. So, that is the first unit operations we took into this course. We listed some of the unit operations which are covered in this course: absorption, distillation, extraction, adsorption, drying, all right. So, now we start with the second part of this second unit operation, which is distillation. So, now you recall, in case of absorption we gave an example of flue gas, sulfur dioxide in air, ammonia in air, H2S in air, carbon dioxide in air, and we bring a solvent, an aqueous phase, and then we separate sulfur dioxide from atmosphere or ammonia from atmosphere into this solvent. So, at the end of the day we have two phases, all right. We start with the pure solvent liquid, and we have A plus B, carrier gas and the impurities, and what we have done, we have transferred one of the components into the solvent. So, all we have done, we have brought a contact, two phases here. We do not give any energy, all right. It is possible that certain absorption could be exothermic in nature. So, some heat may evolve and the process may be non-isothermal, that also happens, but in most of the cases we have nearly uniform temperature in the column, or at least in the calculations which we have done, we have assumed isothermal conditions. So, the mechanism for absorption is based on solubility. You have a gaseous mixture, you bring a solvent in contact and then you remove it, you separate it. Okay. Distillations is another interpretations, where if you ask to separate A from B, then we are not bringing any third component, we bring now energy. So, starting with the liquid or aqueous solutions of A and B, if you want to separate A from B, the mechanism here is relative volatility. A is more volatile than B, or B is more volatile than A, which means at a constant temperature, at a given temperature, A and B, they exert different vapor pressures, which is significantly different in the sense that one can achieve desired separation there. So, start with a liquid, give energy, vaporize. So, now you have liquid vapor mixtures, two phases, A plus B and A plus B. The only thing is the vapor phase will be rich in A and the liquid phase will be rich in B. So, take one stage, take to the second stage, again give an energy, again vaporize the new mixtures. So, you have cascades or trays in the distillation column, where on the top you have a stream of A plus B, but A is nearly pure. In other words, we can have a purity of 99.999%. Theoretically, of course, we can say that A is, that mixture is on the top, A is 100% pure, and at the bottom the liquid is rich in B, lean in A, and we can say that theoretically that B is 100% pure. So, make a difference between the absorption and distillations. Absorption does not involve energy, at least you are not giving any energy there, you are giving a third component. So, we have say desorptions, just reverse of absorptions. We have aqueous mixture of ammonia in dissolved in water. How do we remove? We bring a third component, air. If you bring air, then ammonia gets transferred from the aqueous phase to this air phase. So, our water now becomes pure and pure, but look at the stream vapor phase, now water can also evaporate, vaporize to make the system of A plus B plus C. In case of distillation, we do not bring any third component, we have A plus B, we give energy, substantial amount of energy to cause a separation depending upon the relative volatility of A and B, or the difference between the vapor pressure of A and B. So, we achieve a separations, but now we have both liquid and vapor containing A plus B. Okay. Compare this to evaporations. We have saline solutions, sea water, water containing salt, and what do we do in evaporations? We do give energy, but when we give energy, it is only water which gets vaporized, salt does not get. Unlike in distillations, where we have mixture of A plus B, and if we give energy, we have the vapor phase which also contains A plus B, all right. Slowly and slowly, of course, we make the vapor stream rich in one component and the liquid phase in other components. So, distillations will compare to some extent with the absorptions, maybe in the concept of height of a STU, NTU, or loading and flooding, some of the aspects in what we have covered in absorptions, or the mathematical treatment we did for absorption may be applied for distillation as well, concept of mass transfer coefficients, etc. But distillation, we will have a different treatment, different mathematical treatment to find out the number of trays here, all right. Absorption mostly we did for continuous packed bed columns, and distillation we have stage wise. In practice industrially, it is possible to have absorption in trays wise, and we can also have a distillation in a packed bed column, but those are very, very few cases, and our discussion for this course will be limited for distillation in trays wise, stage wise, and absorption which we did in a continuous packed bed column. So, before we start this mathematical here, let us summarize some of the main points for distillations. Okay. So, we have distillation. So, we say it is also a separation process, separation of components. So, we can have binary components for simplicity, or we can have multi components. So, separation of components from a solution. All right. Now, again when we say solutions, our feed need not be a gas phase, need not be a liquid phase. For example, air, 21% oxygen and 79% nitrogen. All we have to do in distillations, if you want to distill air, we have to liquefy air to the liquid phase and then we do distillations. So, our starting point may be a gaseous phase, but in distillation it has to be liquefied to start with the feed, which could be a pure liquid or could be a mixture of liquid and vapor. So, separation of components from a solution based on their relative volatility. All right. So, this is the mechanism. Here is not a solubility, which we did in case of absorptions. More important here, or also important to note here, is components are present in both phases, which is gas or actually vapor plus liquid. Okay. And another thing here is thermal energy or heat is required to achieve separation. Okay. So, there are three things to note here. One, mechanism here is relative volatility. Second, components are present in both phases. And third, we require this heat to cause these separations. So, if we have start with A plus B in the liquid phase, we have to give energy here, heat. To cause the separations, we have A plus B in the vapor phase. So, there is no third component, all we have component is here heat, which vaporizes this liquid. And when it vaporizes, if A is more volatile than B, that means the vapor pressure of A at any temperature is larger than the vapor pressure of B at the same temperature. Now, we achieve enrichment of this vapor phase with A and small quantities of B. So, this is the way we are going to do it. We take this mixture of A plus B, give them heat, energy, make use of difference in the relative volatility or the vapor pressures to achieve the separations from one level, say Y1 or X1, to in this phase which is rich here, maybe in Y1, Y1 is much larger than X1. Okay. Take this second products, go to the next stage, there again you have A plus B, now starting with different mole fractions here, again give this heat here, again it causes separations A plus B, A is again richer in this component vapor phase, is now richer in A and leaner in B. So, this is a stage wise process here. We can still apply Rawls law, all right. So, Rawls law is applicable to obtain this partial pressure of A as function of mole fractions and the vapor pressure, and also related to the mole fraction in the gas phase, vapor phase and in the liquid phase. All right. So, these are the features of distillation here. Relative volatility, 1, separation is possible, but we have both A plus B present in vapor and the liquid phase. One phase becomes richer in one component which has a higher vapor pressure than the others, and heat is required here. So, compare this to absorption. All right. So, we have now A plus B, say air and SO2, we brought in contact with a third component. So, this is third component, and here one has to be careful, this third component, a solvent should have larger solubility for B, which we want to remove, but we have to bring this third component. No energy, we do not require any addition of energy, although the absorption could be non-isothermal or exothermic. Now, when we have this B A plus B in solvent C now. So, 3 components, A plus B binary components brought in contact with C, B gets transferred here. So, we have C plus B, and there is a possibility of this C getting vaporized. All right. So, what we achieve here, one, look at the difference, sulfur dioxide is getting transferred into this. So, this component, this vapor phase may be linear with sulfur dioxide, okay, but the solvent phase is now getting richer with B here. So, we have one stream where we have A, this A plus B, which contains very small amount of B, but now we have brought this B transfer here by bringing in the third components. In case of distillations, we have A plus B as a liquid phase, give energy, all right, to bring A plus B as a vapor phase, no third components, but now A will be richer than what we have in case of liquid phase, and slowly if we do this, it is possible to do it, obtain theoretically a 100% pure A and 100% pure B. Unlike in absorptions, only one stream can be pure, deprived of the sulfur dioxide, but another stream, another phase is rich with B. So, making difference here in case of absorption and what we have in case of distillations. If you have evaporations, compare this to another unit operations. Evaporations, which you may have done in some other course, mass transfer 1, where we have the salt plus water, all right. You give energy to vaporize, now you have water, salt does not get vaporized. So, we have A plus B, all right, but only B gets transferred from this phase to the vapor phase, liquid, okay. So, you should be able to see a qualitative difference between absorption, distillation, evaporation as different unit operations to achieve this purity. In all 3 cases, we have separations, okay. We want to separate A from B, but the method is different. In one case, it is extensive energy, you have to give extensive energy. So, the heat contents of vapor phase is substantially different from the heat contents of the liquid phase, or A in A plus B has a very larger different heat contents than A in A plus B, unlike in absorptions. In case by distillations, we can have 100% A and 100% B pure theoretically, 99.99%, but look at in case of absorptions, yes, flue gas we have removed, we have made air cleaner in sulfur dioxide, but the liquid phase is highly contaminated with the sulfur dioxide. We cannot take this, dump this spent liquors, one has to bring, take this stream to the desorption. We have taken that example earlier also, to again clean this spent liquor, all right. So, the application is different, that is one. The mechanism is different, in one case is solubility, in one case this is your relative volatility. There has to be a substantial difference in the vapor pressures to achieve this significant amount of distillation or separations, all right. In one case, there is a choice of solvent, I have to bring a good solvent which can remove S2S or SO2. Here there is no third components, it is an energy, it is a very extensive energy process. That is why distillation, you will see when we come to the stage of designing this distillation column or determining this number of trays, there will be 2 approach. One would be enthalpy based approach, one would be species balance or mass balance approach, because there is a difference in the enthalpy or heat contents of the products or the mixture from a stage to a stage. So, by taking keeping track of its change in the enthalpy, one can also decide, one can also evaluate or determine the number of trays, okay. So, so the next topic or the next subtopic for this distillation would be, we must understand vapor liquid equilibrium, because this is what we are going to have. I start with a liquid, 2 components for simplicity, vaporize, you bring another phase, create another phase of vapor which should be in equilibrium with the liquid. So, A plus B in the vapor in equilibrium with A plus B in the liquid phase. So, what is the equilibrium? We decide, of course, again we rely on Raoult's law. Remember Raoult's law we also applied in finding the solubility for assuming it is an ideal solutions, okay. So, Raoult's law can also be applied for this liquid vapor equilibrium, for distillations, and also for liquid vapor or gas liquid solubility, okay. So, we will start with binary component distillations. So, this is for the simplicity, we will focus mostly on binary component distillations, and we will spend a very small a small amount of time on multi-component distillations. First thing is of course degree of freedom, okay, which we know from your previous some course on thermodynamics. Degree of freedom can be written as C minus P plus 2. Components, number of the components, number of phases, number of components, number of phases, all right. So, in our case we have C2, two components A and B. Phase we have 2, liquid and vapor, which means degree of freedom is 2. All it means, if we fix pressure and temperature, then X and Y, mole fraction of A and mole fraction of B, or mole fraction of A in gas phase or vapor phase and the liquid phase, they are fixed, okay, which means fix pressure, vary T, T1, T2, T3, we have the equilibriums between the two phases, vapor liquid, vapor liquid, vapor liquid, but the mole fractions here X, XA and YA, YA, YA XA, YA XA, they are all fixed for different temperatures, because degree of freedom here is 2. Here the requirement is that vapor pressure of A at any temperature should be larger than the other components, okay. So, this is the bottom line for the distillation. There should be a significant difference in the vapor phase. Quantitatively of course we will do the calculation in the coming classes, but the idea here is that one can apply Raoult's law, partial pressure at equilibrium between the two phases, vapor and the liquid, A plus B here and A plus B here. This vapor phase is rich in A and lean in A. Relative to this, it is richer here, and this is lean in B. How? Quantitatively we can calculate as partial pressure of A as YAP equals XA PA0 T, or PB equals 1 minus YA, which is YB, as total pressure equal to 1 minus XA, which is XB, PB0 T, okay. So, fix this P and T, fixing pressure and temperature. We know the vapor pressures of A and B, we have two unknowns XA and YA to calculate from these two equations. So, that is the meaning of degree of freedom. Once we fix the pressure and temperature, mole fraction of A and B, they are fixed in both the phases. Take to the second tray where the temperature is different, you achieve different degree of separations. So, for every pressure, fixed pressure, generally distillation column you will run at a fixed pressures, fixed P, vary T1, T2, T3. For every T1 there is XA1, YA1, XA2, YA2. This is the way YA or component A will become richer in one component. So, vapor will become richer in A, Y1, Y2, Y3, and the liquid will become richer in B, from XB1, XB2, XB3, etc. So, that is your distillations or separation here. In the next class, we will draw this curve, what we call TXY diagram, phase diagram. So, we will do the same calculations, we should be able to show this phase diagram, very similar to what we did in case of absorption when we had this equilibrium curve or the solubility curve. Okay. So, you have very similar approach. First is the thermodynamics. Thermodynamics will tell us, given one phase composition, what is the composition in the second phase. There we have the solubility, here we will make use of this Raoult's law to obtain TXY diagram or YX diagram. Okay. From there we have the equilibrium curve. In case of absorption, we wrote down the operating balance, operating line equations. In case of distillation also, we will write down this operating line curve. Here we have luxury of writing down this operating line equations either in terms of species balance or making use of change in the enthalpy. So, there are two different approaches, because here there is significant change in the temperature from T1, T2, T3, etc. So, given T1, heat contents are different for the liquid phase and for the vapor phase. So, with that, by making use of this property or this feature that enthalpy changes from tray to tray, stage to stage, one can work exclusively on the enthalpy balance. So we have two types of operating curves or two types of approaches. One is based on the species balance, one is based on your or material balance, one is based on your enthalpy balance. So in the next class we'll come back to this. Okay.